My name is Sergey Bratus. I work for Dartmouth College. I'm going to speak about embedded systems as invisible devious devices. And we'll see what that means. And by the way, if you're wondering where Dartmouth College is and what it is, it's up there on the map of the US. I understand your question. We've got quite a lot of geography there. But there it is in the northeast, 2 hours away from Boston. And it's the second oldest college in the US. It also has the distinction of having the oldest non-military engineering school. That is from the time when an engineer had to be able to design a fort and place the cannons properly. That made him a good engineer. The first engineering school, of course, is West Point, the US military academy. So we're going to talk about what embedded systems are and what they stopped being and what this means for us. And I'm going to give you one large war story and a few smaller ones. The larger one is the one that I got directly involved with. And I'm going to quote from Tim Geer, who is a hero of mine ever since the monoculture argument and way before that, actually. So if you look up the definition of an embedded system, you will see that, say, Wikipedia tells you that it's a special purpose computer system designed to perform one of few dedicated functions. This definition is grossly misleading in the modern world. Spot an embedded system on this slide. It's all of them. However, what these things are inside has changed dramatically in the last 10 years. It used to be that your intuitions would tell you that embedded systems, they are everywhere. They are in kiosks, phones, cars, SCADA. So this is the increasing scariness, right? SCADA system, supervisory data acquisition and control. They control things like the power grid. And these used to be small, underpowered, highly specialized computers. And the intuition used to be that if they do what they're supposed to do well, then they're probably working right and you shouldn't fix it if it ain't broke. Now, who could develop for it? Well, developer outfits who could pay for expensive SDKs. And those SDKs were, as a rule, not available to the general public. And these things were not connected to Ethernet networks at all. They used something specialized, such as CAN bus, which is what you have in your car, or the serial, the good old RS-252. And in fact, many power grid computers still use that and ignore the presence of the internet completely. So the intuition is that such a thing would be expensive to exploit and rather low on the list of threats. So that used to be true. Now, these things are primarily based on commodity OSs. So for Linux, Monte Vista is a major vendor. Windows, including Windows XP, plays an increasing role. And I could name you several devices that go into power control grids that run Windows XP Service Pack 2. It was a revelation for me when I was called to look at such a device. But that kind of a thing, an RTU, a remote terminal unit that you see on the screen, that you will now find in your basic power substation. And notice those Ethernet ports, and notice the cute little penguin. Now, I could have put a Windows device there, but I like the look of the penguin more. And as a result, these things run generic kernels. You can customize the Linux kernel if you're developing for these things, if you're building such devices. If you are building it on top of Windows, then you're out of luck. You can't really customize the Windows kernel. What's interesting is that boards are not designed for just narrow applications. The same board that goes into a device like this may go into an entertainment platform. So they are no longer built for your application alone. They are built for a whole range of applications. And programming them has gotten cheaper and faster. It used to be that embedded programmers were wizards who optimized assembly. No more. They're just regular guys these days, who just happen to write for those devices. So, the question is, how often are such devices patched? And I should see you smiling, right?
Once in a lifetime.
So, commodity software brings commodity problems. What you get at bulk price gets you, well, bulk worries. Here is a rather snide quote from SRI concerning Conficker about Sheffield's hospital's operating ward being infested with Conficker. Now, I should see your face roll to go, uh-oh. I mean, an operating ward is where they cut people up and put them back together, right? You really, really don't want any systems in that space to even hiccup, let alone start scanning the network. And there is a fundamental reason for this. And Dan Geer, who is a visionary of IT security, has formulated it pretty succinctly. This is from his talk at Source Boston in March 2009. Lest you think that it is too far-fetched to consider a computer a life form subject to evolution just like any other life form, consider embedded systems. They are already 2 orders of magnitude more numerous than keyboards and displays. Hence, the future threat space is a threat space where a computer is not identifiable as such, but is instead inside some nondescript appliance. So I have to read this because it's too small a font, but it's well worth reading aloud. So there are 2 possible alternatives here. Either an organism adapts, or it dies and makes way for further generations. Adaptation in the devices that don't get breed takes the form of a remote management interface. So in programming, inevitably, you will have late discovered flaws and you will have to fix them, and you cannot go and visit all of those devices. So you will want them connected to some network, to the internet as it were. Without a remote management interface, they are supposed to just die out. With it, they must be able to refuse commands. They must be self-protecting. So what this means for the industry that develops those things is that there has to be a faster evolution, shorter generation lifetimes so that devices could be phased out, cheaper devices, and what this means is that commodity system and libraries are going to play bigger and bigger role. And customization, any customization, just cutting out pieces of code that you don't need is costly. So less and less of this is going to take place. And if you look at an embedded device with software inside, such as the Linux kernel or the Windows kernel, as the device's DNA, you would expect the whole genetic history to be accumulated in that code. Just like natural genome has huge unused areas, so will embedded software. And we'll see that in the example. This is exactly how things are happening. So cutting away things that you think are not used is dangerous. And so the developers don't do that. They do not optimize code for minimum functionality. There is nothing of this least functionality principle that served us so well. They just do whatever is needed to shoehorn a given functionality on the platform, and then the device goes out to the door. One important thing, the most important thing, psychologically, about these devices is that they are innocent looking, right? A Dreamcast that was in fact a scanning machine, a forwarding machine, was demoed at Black Hat DEF CON 2002. It's just like those things that my kids have at home, says someone who sees that sort of thing in his office and just keeps walking, right? A fake UPS, again, this very simple utility. How could this be a computer? This fake UPS actually was hollowed out, contained a board, The problem with both of those examples is that a UPS that's been scooped out to contain a computer no longer provides power. A Dreamcast that phones home from your network is unplayable. So the next advance was made by FX and the Fenolid group from Germany in the printer-copier fax combinations. So modern printers and copiers, they found, contained a whole Java machine, Java virtual machine. And if you cared to program in Java, you could download applets into that virtual machine and run them on your printer. So this is still this is still 2003, right? But now we're much closer to the current state of the art, which is to say, an embedded system today can be compromised, fully controlled, and yet continue to function flawlessly. So you won't be able to detect that it's doing something else by just looking at it when it breaks. So again, I would quote from Dan Geer that the very thing that keeps the device viable as an organism will let the attacker to not only gain control of the device, but also quite likely to help him keep control and be completely unobtrusive, not interfering with the main functionality. And so we come to this. This was a device that I encountered 2 years ago. On our campus network, there are a whole bunch of these deployed. This is a set-top multimedia box. As you can see, there is a TV out. There is also the Ethernet in. So multimedia content such as TV was distributed using that box. And if you open the cover, you'll see this, which is a mini computer. It's an STB, and I'm not at liberty to disclose the make of the device, but it's quite popular. I hear there were deployments of millions of those in Europe, and particularly in Sweden. And so we found that interesting breed of an IP device, talking with a particular port scanning signature while nmapping our network, a little space to do so. There were approximately 400 of them in dorms, offices, lecture halls, the pharmacy. Every time I walk by the pharmacy, I remember where that thing used to sit unobtrusively behind the TV to entertain customers. It's zero configuration. It was supposed to be, you get it, you plug it into any jack, and it works. And it's 100 megabit Ethernet. And of course, it had our remote management interface. And the thing about remote management interfaces is that technicians use them in so many different places. And there is usually a manual on the web, and the manual contains the default password. And changing the default password is actually too much work for deploying technicians. So I'll leave it at that. It was possible to penetrate that box in a number of different ways, but we actually didn't have to do that. What it contained was a Linux kernel 2.4 and a minimal shell with custom applications. Well, the things that were needed to do the multimedia conversion, the IP over the TV over IP in particular, and that had a minimal web server. Most shell commands were removed, so we could log in, we could use the management interface, but there was very little we could do. Most obvious ways to download executables, which is of course the first thing that we tried after we realized what kind of a platform that was and got a hold of an SDK, those most obvious ways were blocked. So you download an executable file, but you can't set executable permissions on it, and so it just sits there. Not fun. There is an SDRAM, and it's mounted on the RAM disk, and we've got 100K of free disk space, which is, again, you can put quite a lot there, and I will describe what we find there. But, you know, kernel configured to reduce memory footprint and the shell environment hardened. So, you know, you got root, but you can ping out, but you haven't got much else. Really not. The kernel was a stock kernel. And what that means is that it had just about anything any other device could want. And this is a standard situation. I can't emphasize this enough. Developers would not go hunting through countless options of the Linux configuration once they know they can fit the kernel comfortably into their SDRAM, into their device, and have it working properly. So instead of removing all those options, they just remove what is necessary and go on making the device something other than a brick. Besides, too much customization would be way too costly and defeat the whole purpose of using the commodity software. So what we found in the kernel was support for the network file system. We could mount shares over the network. We could attach any file system, including with execute privileges, which was actually blocked on the device's own storage. Packet capture. It was all there. The Berkeley packet filter interface, the thing that makes TCP dump and other wonderful packet level tools work. Raw IP and Ethernet. So we could craft any packet, and the kernel would happily cooperate with sending it out. And to craft the packet, you merely need a library, which we got. ARP poisoning and man-in-the-middle attacks on the network, such as provided by tools like DisNIF. IP forwarding was even one, so the device was in fact could be in fact a router. Unfortunately, we could not simply munge the packets because IP tables and NetFilter was not there, but we got around. So the SDK is simply a cross-compiling environment, which took some effort to install, but it's all free. It's GCC, it's back-end, and if it were a Windows device, we wouldn't have fared much worse because it's pretty easy to get a hold of, at least for an attacker, of such development environments for Windows. And we needed some libraries to capture packets, libpcap, to craft packets, libnet, to create SSL man-in-the-middle attacks. So SSL, HTTPS would be what people would use on the same network to connect to their Dartmouth accounts, to their external bank accounts. All of those things are eminently attackable as long as the users disregard the warning about mismatching certificates, which they tend to do. We actually experimented with that. So we took a tool called FragRoute and patched it and patched it and patched it until it became a full router capable of routing packets and filtering packets just like we wanted. And that's the entire tool chain. TCP dump to capture packets, a FragRouter to rewrite them and forward them on, libnet and the ARP poisoner tool, ARP escape, to perform man-in-the-middle attacks and to have packets flow through that box rather than directly from other machines on that network to a gateway. So all of those attacks are not new. They are just simply things that you can do if you have a box on a network that allows ARP poisoning and does not watch for various DNS spoofing and ARP poisoning attacks. So we could get traffic out of the local LAN around any one of those boxes simply by using TCP dump. We were able to do DNS spoofing, man-in-the-middle TCP attacks. In particular, there is a fun one in which all your images turn to something else. I am not going to go further into this, but do not look up that thing on the internet. It's a very, very rude picture. IDS evasion we could also do, because that's actually what frag route is for. And of course, since we had SSL compiled for that box as well, cross-compiled for that box as well, we could do encrypted tunnel. So the only piece that remains, right, is ARP poisoning, which is quite simply accomplished. Basically, ARP is an unauthenticated protocol. This is how devices discover their MAC addresses on the network, and you can easily lie about it. So in the end, our setup ended being like that. The device, which was at the same time showing its multimedia contents perfectly normally, streaming whatever it was, music or TV, to connected TV set. In the background, it was advertising itself to computers on the network as the gateway, and therefore all of the connections, all of the packets destined to the gateway flowed through it. Frag route made sure that they got to their destinations, patched, mangled if necessary. So the only tool that we needed to do some non-trivial coding on was frag route to provide this routing capability, because IP tables, which we wanted to use initially, was not in fact a part of that kernel, unlike NSF and packet filtering and packet capture and all of that. So if you want a penetration testing machine on the network, that was it. And you know, we really didn't need anything else. The 100 megabit interface was fast enough. And so when we Trojan, when we man in the middle download to other machines, you could in fact see some reduction in speed, but nothing out of the ordinary. And well, so we reported this to the vendor, and the vendor came out with the next version of the thing, and we pulled those boxes out of the areas where we're really uncomfortable with having a bot. And just a few days ago, I was looking on the net, and I found this piece of news from a Russian online newspaper, and it was like, "Hello, old friend." So this is the this piece of news related to one large ISP acquiring another for 6 million rubles, which is not pocket change. The acquired party had a large fleet of these devices. The image was taken by the newspaper from the vendor's side, and this is probably a patched version of the device. Probably. So, how hard is this to fix? What is not going to happen is developers trying to cut this extra functionality, which made this thing into such a convenient bot, from the OS kernel. 2,000 plus config options. Developers who understand all that and who have this kind of deep knowledge of Linux kernel architecture come very expensive. You probably are not going to see each and every one of them having that capability. Now, if you're developing on a Windows embedded platform, you're out of luck, because you can't mix and match Windows components. You can certainly try to turn them on and off, just like Enno suggested in the previous talk. But again, you know, how much knowledge does that take? How many components are there? So remote management interfaces will be there. Of course, you can have crypto authentication. But for huge sets of deployed devices, this is really hard. This is the standard key management problem. This is PKI, which has well-known costs, which inevitably turn out to be higher than what they were supposed to be. So the answer is that devices must be self-protected. And there are two ways to do that I can see. And one of these ways we actually implemented in the lab for a voting device that was a voting piece of software that was written in Java and was supposed to run on top of a commodity platform. Well, you can imagine, voting machines are a very sensitive issue. So removing library support, just like the developers of this particular multimedia set-top box have done, is not the answer. Because, of course, you can get your own executables on the machine, one way or another, even in the form of an exploit. And even if the library is absent, even if the shell denies the commands, all the actual work is really done by the kernel, by the system calls of the kernel. And those can be invoked from simple assembly, which is what shellcode used to do since forever. So SELinux provides a way to deny all the system calls that are not needed by an application and change that profile based on the type of the application. So when you start the very first process after boot, which is called init, and it spawns children, those children get specific type labels as described by the system based on their ancestry, so on the parent process and on what binary executable was used to create the process. And only the minimal set of system calls is allowed. So it's like a straitjacket for a process. And with that, even if you have the functionality in the kernel, you can prevent it from being ever activated by one of the processes that is allowed to run on the device. So the goal, the exploiter goal is still there, but you prevent access. Another way has solidified recently. OpenSolaris came up with an easily programmable tracing system, a system-wide scripting language and mechanism that would take that scripting language that worked in the kernel, which could intercept just about any programming event that the programmer could think of. System calls with specific arguments, system calls and process context. So if something that you know should not happen on the device does happen, you have the option of activating a particular probe and rebooting the device, returning it into a known good state. So the new thing in dtrace was a very low performance penalty. Unlike virtual machines, unlike debuggers, that thing is inactive until hit for every probe. And even then, it provides very limited performance here. And Linux is catching up with a system called kprobes and a scripting system called systemtap sitting on top of it. So if your developers have a clear understanding of what things the processes on the box should not do, they can easily, and that is the key word, easily and cheaply, code a script for a trace-based watchdog. And if I were operating a set of a large fleet of embedded devices, I would require one of these two solutions. The problem with embedded devices is not new. So the Risks Digest from 1996, Peter Neumann, has these wonderful items. A phone call deluge from a program bug in a computerized Coke machine. A Coke machine calling mothership for update, for reloads, accidentally got the phone number of US Army Fort Bragg. So this is an actual picture from US Army Fort Bragg, and a Coke machine was calling it day and night. So the US Army certainly has the capabilities to track down an annoying caller like that. And imagine how they were surprised when it turned out to be one of those red things. But these days, they use TCP/IP. And this is actually interesting because a certain virus, as late as 2001, the so-called E911 virus, was actually programmed to make 911 emergency number calls and could, in fact, interfere with critical operations of, say, a local police department. Here's another one that I had to deal with. It was a strange, persistent port scan from the part of the building where we did not have any Windows computers at all. That was in the time of Code Red and such like fun. It was incredibly hard to track because, I mean, there's nothing there, and yet the port scans keep coming. Our admins tracked the cables, and again, they found nothing much. What it turned out to be was a digital panel, a picture frame that had a Wi-Fi capability, joined the campus network, which was open at the time, and happily got infected with a worm. It was an old version of Windows C, and it, kept the good work of scanning our network until it was finally tracked down and deactivated. So, of course, the next generation of embedded systems is going to be everything we ever read about in sci-fi books, right? Of course, one of the things that we read about in sci-fi books, as early as in 1984 in William Gibson's Neuromancer, and I think enough for this reference, was a story about how an AI, supercomputer intelligence, turned gardening robots into killing machines, because the things that trim hedges can cut humans too. And rescued the main character out of a tight spot. But this is really scary. I mean, I would be less afraid of garden robots coming after me with their hedge trimmers, but I am really afraid of SCADA devices being inadvertently exposed to network traffic that's destined to the corporate side of, say, a power utility, and then taking on a virus. So some of the work I've done was in fuzzing our SCADA devices, and I can tell you those were not any sort of thing that I could ever buy on eBay to play with. This was in an isolated control environment that was set up by our partners in the power industry. Expensive stuff, very, very trusting as to the input in the protocols. So I would never want something like that on a standard corporate network with Windows machines downloading ActiveX controls, and then or PDF documents with JavaScripts, and then carrying on the scans. Because these protocols are quite brittle, and although those things are designed to reestablish connections, that's actually one of the things that could provide for a very efficient denial of service attack. You could have a device rebooting all the time. So these are the things that keep up the lights, right? So for the conclusions, I hope I have scared you enough, and if you're responsible for a large network, you will chase down those embedded devices and just find out what is it that they can do based on the software that's in them. So embedded no longer means too specialized to allow reliable and transparent hacks. No. Now these devices are commodity OSs, and they can support just about any kind of activity. If it's got a network interface, it's got a full TCP/IP stack. That full TCP/IP stack probably comes with support for all sorts of interesting protocols. Those protocols have bugs. They can be triggered by remote traffic. This is as true for Linux as it is for Windows. In fact, it's actually truer for Windows because Windows comes in one large big bundle, and developers cannot really do anything much about it in the way of cutting it down, as they might attempt with Linux. Watch out for these invisible devices. Know their OS and know if they can be patched. If they cannot be patched, they have no place on a network that has any flavor of public. And consider using something of the advanced OS techniques, such as SELinux or a tracing watchdog, if you can afford to dictate your terms to a vendor, or if you can, if you have your own programmers who can deploy it. And with that, I thank you for your attention. This is the bell tower of the library of our college. A president of Dartmouth has spent some time in Cambridge, UK, and brought back, well, a tower and a clock. Which I find to be one of the most enjoyable aspects of life on campus. Thank you.
Okay.
Yes.
One question.
Yes.
How common are these multimedia devices you're focused on during the man-in-the-middle attack? Is there a 1-to-1 ratio, or can you also use it as a gateway for a /24 network at a man-in-the-middle attack?
Under low loads, yes. Under heavy loads, you will see some packet loss.
Okay.
I mean, it's an STB, which is IBM's STB, which is a nice platform. It was actually quite efficient as a router.
Okay.
Like I said, we made some measurements for user perceptibility of such a device sitting in the middle of a large download. And yes, there was a 1.5 decrease in speed on our network. But that is not something that a regular user would actually go complaining about. Perhaps after a week, but not right away.
Okay, thank you.
Any more questions? Well, thank you very much.